This video will focus on two learning targets, both having to do with graphs. So number one, I can interpret a phase diagram, and then number two, I can explain how energy is used and changes during phase changes, and we'll use heating curves to kind of explain that. So now that we've looked at all three states of matter, solids, liquids, and gases, I can show you something that's called a phase diagram. And what this is a representation of the different states of matter for any substance given the conditions of pressure and temperature. Okay. As you know, there are boiling points and freezing points for all substances, but those are usually based on a standard temperature and pressure, generally spoken about as room temperature and room pressure. So 1 atm and either 25 degrees Celsius or 0 degrees Celsius, depending on what standard state we're using. What this diagram represents then is at any pressure and at any temperature, what state of matter am I going to be in? Because you saw the demonstration where I was able to create a gas from a liquid when it was colder than 100 degrees Celsius. Okay, so that's what this phase diagram represents. It represents information about when pressure changes and when temperature changes, how that affects states of matter. As I've already said, pressure will greatly affect the gas kind of phase, and it doesn't affect the solids and liquids quite as much, but it still can have a relationship. So if you look at this diagram, what you have is a region of the graph where your matter will be solid, a region where it will be liquid, and a region where it will be gas. So for solids, our region is over around the solid inside this line, liquids in the middle inside those lines, and vapor down here inside those lines. What each of these lines represent then is the phase change. So when you go from a solid to a liquid, this line represents the melting point. When you go from a liquid to a gas, this line represents the boiling point. Down here we have from solid to vapor. That happens too. That's called sublimation. So you also have a sublimation point where you go from a solid straight to a gas given certain conditions. This graph contains 2 points to take note of, a triple point and a critical point. The triple point is the point at which all 3 states of matter are happening simultaneously. So we have the transition from both melting and boiling and sublimating happening simultaneously. So the triple point is this weird state of matter where you have both solid, liquid, and gas all in one container. The other point of note is this critical point, and what you can see about the critical point is that the line between gas and liquid doesn't extend beyond the critical point. What that means then is you can't change the temperature and change the pressure to change your gas back into a liquid, essentially. So once I've exceeded the temperature of the critical point, I can't increase my pressure to get it back into a liquid. Or I can't, once I've exceeded my pressure of the critical point, I can't decrease my temperature to get it back to a liquid. So at this point, it's that you really just have a gas all the time. If you increase the pressure or decrease the temperature, you'll just have like a colder gas or a highly compressed gas, but you won't have a liquid. In class on Tuesday, we'll spend a little bit of time reading data off of here, so knowing how to affect the phase change based on these diagrams, but essentially you just need to be able to read them and use them. The other graph I'm going to show you is something that's called a heating curve. So a phase change diagram has to do with looking at the phase changes as it relates to pressure and temperature. A heating curve, on the other hand, is looking at a substance at a constant pressure and varying the temperature. And as the temperature increases on that substance, noting what it does to the phase it's in. So I'm going to show you a quick clip that relates to this, and that'll be pretty much it.
When heat is applied to a solid, its temperature and vapor pressure increase with increasing temperature because the molecules of the solid have increasing kinetic energy. At the melting temperature, heat is absorbed as the solid is converted to liquid at a constant temperature. When melting is complete, the temperature of the liquid and its vapor pressure increase. At the boiling point, temperature remains constant as heat is absorbed to convert the liquid to the gas phase. When all the molecules are in the gas phase, the temperature again increases as the gas phase molecules acquire additional kinetic energy. On this graph of time versus temperature, the first segment represents heating of the solid. At point A, the solid melts. The temperature remains constant while melting occurs. At B, all the solid has melted, and the temperature again increases as the liquid is heated. At C, the liquid boils. Again, temperature remains constant with time until all the liquid has been converted to gas at point D. Then temperature again increases as the gas is heated.
If you take a second to think about that simulation, you'll be confronted with something that really goes against everything you understand about nature. And that is the fact that as you heat up substances, when a substance is undergoing a phase change, so when it is melting or when it is boiling, the substance itself does not change its temperature. All it does is change the state of matter it's in. So if you look at a heating curve, down here you have when you have a solid, and if you heat up that solid, if you put more energy in, the solid will increase in temperature. But as you melt, take a look at that graph. It is totally flat, which means you are continuing to input energy into the substance, and the substance is not changing. It's something you know. Think about it, because you know that the melting point is at 0 degrees Celsius, right? Which means all of the substance melts at 0 degrees Celsius. Now, if you saw something melt, as we spoke in class at one point, all it doesn't melt instantaneously, it takes time, and that's shown in this graph. You have to input energy into the substance without the substance changing temperature. It is going from a solid to a liquid at 0 degrees Celsius. Right? So what is that energy going to do? If you think about the relationship between energy and temperature, we know temperature is a measure of average kinetic energy. So if our particles move more, they will be hotter. So anytime we have a slope here, like an increasing slope, we know those particles are moving faster as the energy is inputted. But here, every time we have a flat part of our graph, we know our particles aren't moving faster even though we're putting in energy. So that means this energy is not going to change the kinetic energy of the material, it's going to something else. And it's going to something we've talked about in class multiple times, and that are those intermolecular forces. What's happening at these flat parts is not that the particles are speeding up, it's that the particles are spacing out. So when I look at this graph, I think of speed, space, speed, space, speed. The other thing to take note of is just the magnitude of the phase change when it comes to boiling and the phase change when it comes to melting. Okay? If you think about ice melting, in the span of not too long, all of your ice in a glass will melt. But if you think about something boiling, if you're boiling a pan of water, you never see it all go from a liquid to a gas unless you are doing something by accident. The majority of it stays in liquid phase. So this graph shows you also the magnitude of a phase change. It is much easier to melt something and much harder to evaporate it simply based on the amount of energy needed to do this.